So in today's class, basically, we will see the last topic of third unit, basically, that is field effect transistors, FETs as a variable register. So here we will see the analysis of FETs. So here basically we have seen two different type of FETs. So one is JFET, another one is Mosfet. So in both the cases, we have seen a different characteristics, input and output characteristics in case of JFET, and also in case of Mosfet. So in between those characteristics, we have with different type of regions in which the MOS is to work or the FETs work. Basically, so region of operation, we have found it out where these MOSFETs or these FETs, JFETs and MOSFETs, will be behaving like a register. Okay, so characteristics of a register is, so if a register is there, so its characteristics is like it will be following Ohm's law. So what is the meaning of Ohm's law? So Ohm's law states that the voltage will be directly proportional to the current. So the voltage across a device will be directly proportional to the current. Okay, and if we equate it, so its proportionality constant will be a resistance, or the resistance will be V by I. So this resistance will be voltage divided by current will be a constant, or we can call the relation between voltage and current will be directly proportional. So the voltage is directly proportional to current, or in one another state we can call it like the variation in voltage with respect to current is linear. Okay, so V and I are linear or linearly related. So any variable that is linearly related, here the variables are voltage and currents. Okay, so if the relation between voltage and current is linear, in that case we will be calling like the voltage divided by current will be a constant. That constant will be nothing but a resistance. Okay, so the similar concept we will be applying of FETs. So FETs we have seen JFETs, Mosfets. So we will see how this JFET and Mosfet can. So variable resistance means a resistor with a variable sign, like it variable, and this variability will be based on the some controlling voltage. Okay, some controlling voltage will be there. So this variation is based on controlling voltage. So here that's why the FETs are called FETs can be used as a variable resistance dependent resistor, a variable resistor, or we can also call as voltage dependent resistor. See, repeat first. Okay, so the first we will see G. So here we have already seen the characteristics of JFET. Now JFET, where is output character, the output characteristic initially, so what is it initially 0 is reverse biased, and is initially gate to source is 0 and then it is biased. Once we it is gate time to current, the maximum current will, and as we are to increase voltage in negative direction, going to reduce, so it is reducing. So there is a region, so this region initially where the current and voltage relation is seems to is ohmic region, and this region is called your saturation region. Okay, so in case of ohmic region, we will just the operation of this JFET, that will be reduced somewhat the operation of volt register, where the VI ratio, if we find out constant, or we can from here the voltage is nearly related with the current in this region, it will be having a resistor. This is the region where ohmic region or linear region. Linear region means the current and voltage has the that will be lower relation. Okay, they are linearly related. Then we will be called it is behaving like a register. Okay, so we can see here, look a closer look to this, and this is the how the voltage different bias are here. So we are applying is a negative gate source biased based on this gate to source voltage going to vary. So if the relation we call it, this is so suppose for one ID versus for another value, this is the relation, and for next this is the different graphs are there. Okay, so with respect to that, whatever the slope is there, so this is the slope, that is if we plot the slope, or we can call it this is the slope, suppose this is 1 2 and 3, the slope 1 will be looking like it is higher value. Okay, so slope is greater than the slope 2 is greater than the slope 3. Okay, so this is having the lower slope, so we can just correlate in terms of voltage, and slope will be output, or we can call it like here the slope we are evaluating, that will be equals to the id divided by id1 divided by vds1, that will be greater than id2 ds2 id3 divided by 3. So of here so the relation current and the voltage and is given resistance, v will be from there, I by v will be 1 by r. Okay, so here this is 1 by r1, you can call it, is greater than 1 by r2, is greater than 1 by r3. So this is 1 by r1, so 1 by r1 is considered as gm, transconductance. Okay, so gm1 will be greater than gm2, gm3. So in terms of here we can correlate relation of id versus vds in terms of resistance. So if we to this region, it will be showing that in this relation we are having different q points. So these are q points are different. This is DC load line, this is DC load line. So if this is the DC load line, then the different Q points. So for these different Q points, we will be having different resistance. Okay, so these resistances are having the difference variations because of the change in voltage. So because of change in VDS, so this is VDS. So if we are going to have a change in VDS, there will be a change in these resistance values. So at this point, we will be calculating the slope. At this point, we will be calculating a slope. At this point, we will be calculating a slope. So we will be having different resistances or different transconductance, we can call it. So here, by varying the drain to source voltage, there is a variation in the resistance value. So that's why these JFETs can be behave like a voltage dependent resistor. Okay, so to have a JFET operating as dependent resistors, we need to bias these JFETs such that it is going to be operating in linear range. Okay, or it will be at the start of this linear region. At that time, the VDS should be very less compared to VGS what we are applying. So VGS is greater high in case of VDS less. At time there the voltage and current relation will be linear. Okay, so this is the case of JFET where it is going to be behaving like a linear device. There it will be behaving like a resistor. So in that structure also we have discussed already. Okay, so this was the structure. Here the gate is there, this is drain and this is source, and this is biased positive and this is biased negative in case of JFET, gate, drain and source. So we have discussed also, like if gate to source voltage is suppose 0 is there, so if we are applying this is suppose 0, at that time there will be some depletion layer here. Okay, and with respect to that there will be a current because this is 0, then there will be a flow of charges from this because this is positively connected. So this is n channel is there, so it is n type. So the electrons available in this n type, that is in majority, that will be attracted towards here. So electron movement will be this way, the current direction will be this way. Okay, so electrons will be attracted here. So based on the applied field or applied voltage, there will be different voltage variations. So at this point there will be different voltage. So suppose this is V1, this is V2, with V3. So these voltages will be nothing but the voltage drop across the resistive path occurred by this channel region. Okay, so this channel will be at that time behaving like a resistance region or resistance path where there will be different voltage drops are there. So this voltage drop will be suppose 5 volt, this will be less than, that is 4 volt, this is 3 volt. Okay. So at that point, if we consider this path, it will be having low resistance. If we consider this whole path, it will be having higher resistance. So this is behaving like resistance when we have biased it in such a way that it is going to work for the case where VDS is less. Okay, and also if we are going to bias such that the VGS is even higher or even greater, then it will be behaving like a linear region. Okay, so this is the basic concept of FETs or JFET, basically behaving like a variable resistance. So variability will be based on the gate to source voltage. So if we are going to have the gate to source voltage higher, okay, gate to source voltage is in negative direction, we will be getting like the slope is going to reduce. So slope is going to reduce means GM is going to reduce. So GM is transconductance. So here this is transconductance So transconductance will be reducing if we are going to increase the VGS in negative direction. Okay. So this is how the JFET is going to be behaving like a voltage dependent resistor or variable resistor. Next is we will be seeing the MOSFETs. So MOSFETs can also be behaving like a resistor. So in that MOSFETs, so this is the MOSFET. Here only three terminals are shown. Body is connected to, you can say, if it is N channel, it is connected to source. If it is P channel or P MOSFET, it will connect to higher potential resistor. Okay, so this is your MOSFET. In that case, it will be equivalent to a variable resistance, and this equivalence will be based on the gate to source voltage. Whatever gate to source voltage we are applying, based on that there will be variation in the resistance. So this resistance is between the source and drain. So source and drain, if we consider the MOSFET, if this is the MOSFET, so this is your source region, this is gate and drain. So between source and drain there will be a resistance. So that resistance will be because of the channel region only. Okay, so in this channel region, because of the channel region only, there will be a resistance path coming out between source and drain, and this resistance will be depending on the gate to source voltage. So gate to source voltage will be controlling the resistance value. That's why it is a variable resistance with the gate control is shown here. So similar is the case in JFET also. So in this case of MOSFET, again we have seen the MOSFET characteristics. So it was increasing. So MOSFET characteristics was, so if you plot the ID versus VDS, it was again having this relation. Okay, so the region where the ID versus VGS is having a linear relation, we will consider that in the case of where the MOSFET will be having like a voltage dependent resistor. So if we zoom out, we can see there is for different gate to source voltage. So this is for different gate to source voltage. Okay, so this gate to source voltage 3 is higher, this is lower. So this is the relation between ID and VDS. So here for different gate to source voltage, it is having different slopes. So different slopes are nothing but the different resistance value or different transconductance in terms of. So this will be occurring only because this is the saturation region and this is your linear region. So this will be occurring in the linear region itself. So the condition for linear region we have already seen. So condition for linear region is gate to source voltage should be greater than VTS, and at that time VDS should be less than VGS minus VT. So we have seen this condition for case of the linear region. So linear is also called triode region. Okay, or we can call it the ohmic region also, but basically it is called linear or triode. Okay, so this was the condition. So in that case, if it is going to be behaving like a variable resistor, so here again drain to source voltage is going to be very less, okay, compared to the gate to source voltage. So here, so the condition for this region where the MOSFET will be having like a variable resistance is called deep triode region. So this was the region of triode region. So into the deep, so at the starting of the you can say triode region is considered to be a deep triode region. So there is a condition for deep triode region. So in deep triode region, MOSFET behaves as variable resistance resistor, or we call it voltage dependent resistor. So in deep triode region, this will be the case. So the condition for deep triode is basically so first of all we will see the current equation in case of linear region. So current equation RD in case of linear region we have seen if it is n Mos, so mu n Cox W by L into the bracket VGS minus VT. VT is basically here it is VTH. Okay, this is threshold voltage. So threshold voltage, this is not thermal voltage. So VT we have already seen thermal voltage. So do not confuse with that. This is VTH. This is threshold voltage of Mosfet, and VT we have already seen. VT is kV by Q or T 11,600. This so this is thermal voltage. So this is different. Okay. So this is not. This is called thermal voltage, and this is VTH is called threshold voltage. So we are talking about the threshold voltage of Mosfet. So this is mu1 Cox W by L VGS minus VT into VDS minus VDS whole square divided by 2. So this is the current equation in case of linear region. So in the condition for triode region is that here we can see from here the ID versus VDS curve. The VDS is very less, then only deep triode region will be considered. So in that case it is considered like the VDS is considered less than 2 times VGS minus VT. So if this is the case, then it is called the deep triode region. Okay. So deep triode region will be the region where the Mosfet will be behaving like voltage dependent resistance. Okay. Also, in that case, if this is the case like VDS is considered to be very less than 2 times VGS minus VT. So if this is condition called condition for deep triode region. If this is the condition satisfying, then it will be considered as the deep triode region. So this deep triode region is part of the linear region. So this condition we will be putting into the current equation for the linear region. So we can just see how it basically behaves. So if we are going to put here, so the ID you can see RD linear will be mu n Cox W by L. We will be just expanding it. So it is VGS minus VTH multiplied by VDS 2 times here minus VD divided by 2. So we can come here. So for deep triode region should be less than 2 times VGS minus VT. That means this is 2 times VGS minus VT. So the VDS that is there, this VDS is even less than this value. So less than this value, or we can just consider one step more. That is mu n Cox W by L. From there, VDS we can take common. So VDS, if we are taking common, what will be remaining? VGS minus VTS minus VDS divided 2 will be considered outside here. Okay, so this is the condition. So in deep triode region, the condition of triode region comes from here. So if considerations VDS is even less than, you can consider very less than 2 times VGS minus VT. If this is the case, that means in comparison to this term will be neglected, because this is very less than 2 times VGS minus VT. So if this is the case, we will be neglecting this term. So neglecting this term means we will be making it to 0, and then we will proceed with like mu n cox w by L, this is 1 by 2 outside, into VDS multiplied by 2 times VGS minus VTH. So we have neglected this term. So if we arrange it, it will be like 1 by 2 mu n cox, this is L, to VTH into VDS, we can write. So this 2 and 2 will be cancelled. So the ID mu x minus V. So this in the case triode region, that is, we find out the current is the current in deep triode region. So if okay, so here will be voltage divided by so from the find out, so VDS ID put 1 by, here it will be 1 mu n cox w by L VGS minus VTH. So be the resistance. So this resistance value is called on resistance. So R on will be 1 upon mu n cox L minus. So this is the for deep triode region resistance or the on resistance. So that means, so if we see the ID versus VDS, so this ID versus VDS is output characteristics of Mosfet. So at the start of the operation, when the current flow starts, that means the Mosfet to on. Mosfet is on means VGS greater than VT. So the Mosfet is on, that means VGS is greater than VTH threshold voltage. So if VGS is greater than VTH, we can call it like Mosfet is on. So if Mosfet is on, instead of using a short circuit, so if Mosfet is there and if it is on, we generally use like it is short circuit, but it is not a short circuit. Instead of a short circuit, what we will be using is, if it is a critical MOSFET, there will be a resistance if it is on. Okay, so if it is on, there will be a resistance across it, and that resistance will be R on. So this R on is the resistance when MOSFET is on. That means there is a current flowing through the MOSFET. That means there is a VGS greater than VTH, and also the condition like the VDS should be very less than 2 times VGS minus VTH. If this is the condition, this is for deep triode region. In that case, there will be a resistance, this, and current will be this one. Okay, and this VGS minus VTH is also called overdrive voltage. Overdrive voltage means, so VGS, that is VTH, was required to drive the MOSFET, but if we are applying VGS that is greater than VT, that means whatever VGS greater than VT is there, that will be an extra voltage, that is overdrive voltage to the MOSFET. So MOSFET was requiring only VTH to turn on the MOSFET, but if we are applying the VGS that is greater than the VT, that means VGS minus VT will be extra voltage, that is overdrive voltage in case of overdrive voltage of MOSFET. So from there we can just see R on depends on different parameters. So one is like mu n and cox. These are you can say fabrication parameter. Okay, or called process parameters. That is, we can just call it the fabrication parameters. Okay, so these fabrication parameters are decided when the device is going to be fabricated. At that time only the cox, that is oxide capacitance, will be based on height thickness. That is dependent on the fabrication. Then one is W by L. So W by L is also called aspect ratio. So it will be depending on aspect ratio, that is W by L. The third term is the VGS minus VTH. So VGS minus VTH is called overdrive voltage. That is VGS minus VTH. So this is how the MOSFET behaves like a voltage dependent resistor. So its equivalent circuit we have already seen. So equivalent circuit will be a resistance with controlling gate. So there will be gate to source voltage. Resistance will be on, and that will be depending on the gate to source voltage. Okay, so till now, if anyone is having any query, you can ask. So this is all about your unit third. So from next class, topic of unit 4, that is operational amplifiers. So how these operational amplifiers are basically operated as a different. Why, first of all, why it is called operational amplifier, and what are the different use of these operational amplifiers in case of mathematical operations. So that part we'll see into the 4th unit. So till now, if anyone is having any query, you can ask. Okay, so one more announcement is like, as the unit 3rd is completed, we will be having a quiz for this unit 3rd. So the quiz will be taking place between Saturday and Sunday. Okay. So in between Saturday and Sunday, we will be having a quiz. So you all should be prepared for that. So either on Saturday or Sunday, we will be having a quiz for the 3rd unit only. Okay. So just go with the concepts, whatever we have discussed into the class, and based on that, there will be a quiz. So that quiz will be having 10 questions, and you will be given 10 minutes for that. So if anyone is having any query, you can ask, otherwise we will be closing.